Hi. So let's see, we're going to be doing a problem based on analyzing forces. I'm starting out with this slide, which we have seen before, potentially anyway. So what is this? This is our steps for force problems. We start out by drawing a free body diagram. We define our X and Y directions based on that free body diagram. We break the forces that don't point in either X or Y into X and Y components. And then we apply Newton's second law in the X and Y directions based on that free body diagram. That was really quick, but we have talked about this before. Okay, so let's see the specific problem that I want to do in this video. This says we've got a mover trying to push a box across the floor. The box has a mass of 50 kilograms. It says the coefficient of static friction between the floor and the box is 0.4. And it says that the mover pushes with a force of 80 newtons. And we're asked a couple of questions. We're asked, does the box move? And if the box doesn't move, what is the frictional force resisting the motion? All right, so we'll start out just by drawing a little picture here to try to represent the box. There we go. There's a box on the floor. There's a little mover. There we go. Trying to push the box to the right. And we're asked, does the box move? Okay. So we've got our picture. We can now picture that in our heads. And what I want to do is the first step of my problem solving process, which is to draw a free body diagram. And rather than me doing that right off the bat, I have a list of possibilities here that I would like you to consider. Let's see here. I will say that for sure, only one of these is correct. So I want you to pause the video for just a second and see if you can figure out which one might be right. So pause. Okay, so this one is the correct one. Why is that one the correct one? Because gravity is going to pull the box down. The ground is going to, of course, keep the box from falling through it. So the Y forces have to be balanced with each other. So the Y forces have to be the exact same size. Okay, so there and there. Okay. All right, and then let's see, the mover pushes the box to the right. Okay, so we've got that. And the friction force is going to resist that push. Okay, so we have to have these, the forces in the Y direction balance, which that eliminates this one right there because those forces aren't balanced. Okay, and then we definitely have to have the mover pushing to the right. So we don't have that in those two. So those two are just incorrect. All right, so given the fact that we've got our free body diagram now, let's try and solve the problem. First step, free body diagram. Second step, decide on X and Y directions. Well, for this particular problem, this is really easy. We just keep the X going to the right and the Y going straight up. So that's taken care of. Step 3 in that problem solving process was, let's see, break any forces that don't point in X or Y up into X and Y components. But all of these either point in X or in Y, so we're good with that. Step number 4 was to do Newton's second law in the X and Y directions. So let's go ahead and see if we can proceed a little bit with that. Of course, these steps are just guidelines. They're, that sometimes they are really useful. Other times they are maybe not as useful, but they are good guidelines to keep in mind when we're faced with force problems. All right, so let's see here. Let's start out by looking at the Y direction. The sum of the forces in the Y direction is equal to mass times acceleration in Y. Okay. Are we going to have any acceleration in the Y direction at all? Does our box move in the Y direction? Well, no, absolutely not. Our box is not moving, nor is it accelerating in the Y direction. So that's going to be 0. So the right-hand side of this equation is going to be 0. On the left-hand side, it's asking us to fill in all the forces that act in the Y direction. Well, in the Y direction, I've got the ground pushing on the box upwards, and then I've got the box's weight downwards, and that sums to 0. And so what's this telling me then? This is telling me just that the normal that the ground pushes on the box with is going to be equivalent in size to the box's weight. The box had a mass of 50 kilograms, and G is 9.8 meters per second squared. And so when I multiply those two numbers together, I get 490 newtons. 490. Good enough. All right. In a prior video, we learned that the maximum size static frictional force is equal to mu sub s times the normal force. So if I'm concerned about the frictional force that the floor exerts on the box, its maximum size is going to be equal to the coefficient of static friction times the normal force that the floor exerts on the box. Notice here that the friction and the normal force, those two are always linked, and it's always the same thing acting on the same thing. So it's floor on box for the friction force, it's floor on box for the normal force. So if I want the friction the floor exerts on the box, I need to use the normal force that the floor exerts on the box. Our maximum size frictional force is going to be equal to the coefficient of friction times my 490 newtons. And that gives us 196 newtons as a result of our maximum size frictional force. That's just bad enough that I want to erase it. There we go. There we go. 196. So that's the maximum size frictional force that we had. Now, how much was the mover pushing with in this problem statement? It said that the mover pushed with a force of 80 newtons. All right, so the mover's only pushing with a force of 80 newtons. That's definitely not enough to overcome that maximum size friction force of 196 newtons. So the box does not move. So the box doesn't move, does not move. Awesome. Now, the next question that we had was, if the box doesn't move, what's the size of the frictional force that's acting on the box? Well, the mover's pushing with a force of 80 newtons. And so how much is friction going to resist the mover's push? Well, it's going to resist the mover's push with that exact same size force, a force of 80 newtons. Well, you can say, well, I'm a little bit confused here. You know, Dr. Houston, you just said that the maximum size static friction force is 196. Well, that's true, but that's the maximum size static friction force. If I only push a little bit on the box, then the frictional force is only going to be enough to match that little bit that I push. As I increase the size of my push, the size of the static friction resisting that push is going to increase until I get all the way up to 196 newtons. And if I push with more than 196 newtons worth of force, then the box is going to start to move. So the answer here is if the mover pushes the box with a force of 80 newtons, then the frictional force of the floor on the box is going to exactly match that. It's going to be 80 newtons. Now think about physically what we would be saying if we were to say that the frictional force was actually 196. That would mean that the mover's pushing with a force of 80 newtons to the right, and the friction force is pushing with a force of 196 newtons to the left. Well, the friction force would be bigger than the force that the mover's pushing with, and that would tell us that friction is making the box move to the left, which that doesn't work. So that would be kind of the silly result of making a mistake of saying, well, the floor is exerting a force of 196 newtons on the box. That's not true. The floor is just exerting a large enough static frictional force to match the force that the mover is pushing with. All right. So there's a follow-up question here, though, that says, what if my mover actually pushes with 196 newtons worth of force? Maybe I should have written 196.1 so that it's just enough to break the box free of static friction and get this box moving. So given the fact that the mover has done that and continues to push with its force of 196 newtons, what is the box's acceleration? So that's our question that we're seeking to answer in this particular slide. What is the box's acceleration? Okay. All right, if now I'm pushed with enough force to get this box moving. And now because of the fact that the box is moving, now I've got kinetic friction, moving friction between the box and the floor rather than static friction. And now I've got a new value for my coefficient of friction. My coefficient of kinetic friction is what? It's 0.35. Okay, so there's my question. First step, free body diagram. And this free body diagram looks a lot like the prior one. We've got a weight force downwards. We've got a normal force from the floor pushing on the box, floor on box. There we go. We've got a, let's see, much larger normal force of the mover pushing on the box. Then there is a static friction or a kinetic friction force of the floor pushing on the box. All right. So my forces in the Y direction there should be balanced. My mover's force is going to be larger than the kinetic friction force. All right. So there we are. Let's go through and do the mathematical analysis that arises from this. Okay. Okay. So we already did the Y direction for the box. And when we did the Y direction for the box, we figured out that the normal force that the floor exerts on the box is equal to the box's weight. That's 490 newtons. Okay. So that's the same as the prior problem. Nothing has changed about the Y direction at all. In the X direction, the sum of the forces in the X direction is equal to mass times acceleration in the X direction. We have, let's see, the force that the mover exerts on the box to the right minus the kinetic friction force that the floor exerts on the box to the left. And that's going to be equal to the box's mass times its acceleration. We said here, well, we've got a number for this. This is 196 newtons. And then friction is, what is friction? Friction is fun. There we go, fun. The coefficient of kinetic friction is 0.35. The normal force of the floor on the box is 490. And that's going to be equal to the box's mass times its acceleration. Okay, there we go. And then if I drop my calculator, if I plug the numbers into my calculator and get out the result here, I will see that I've got a bad number. Sorry about that. I will see that I've got 24.5 newtons is equal to 50 kilograms times my acceleration in the X direction. If I divide both sides by 50, I get my acceleration of the box. It looks like the box has an acceleration of 0.49 meters per second squared in the X direction. And that is the answer for that. Okay. I hope this all made sense. And we'll maybe see you in another video.